Okay, welcome back to Lesson 7. This is our last lesson in Unit 6 of our AP Calculus course. This lesson is just called More Practice Using Derivatives Analytically. So I really want us to focus on theory, and we'll mix in a little bit of skill review as well. But I want to review our theory of calculus and how it works, and make sure that we are all on board with what these theorems are really saying. So let's start with this example. We're going to evaluate the following limit giving the following functions. G of x is equal to x minus 2 squared, and f of x is the function shown in the graph. So we'll evaluate the limit as x approaches 2. Well, clearly g of 2 would be 0, and f of 2 is also 0. So how would we end up evaluating this? Well, we can use what we just learned in the previous lesson. So we'll show that the limit as x approaches 2 of g of x is 0. And the limit as x approaches 2 of f of x, well, that's also 0, right? So by L'Hopital's rule, we ought to be able to say that this limit is equal to the limit as x approaches 2 of g prime of x over f prime of x. Well, what is g prime? Well, we'll have to find that. Okay, so that's 2 times x minus 2, and then times the derivative of the inside, which is just times 1. All right, and so we can see now that g prime of 2 is 0. F prime of 2, though, is the slope of f at 2, which is, I think, a negative 2 over 1. So it's a negative 2. So we can see that the limit is actually 0. All right, you try this practice problem. All right, let's see what we did here. Okay, I'm not really sure why this is so far down here. I'm going to move that up there, give myself a little bit of room here. Okay, so we got a table here, and we're going to evaluate this limit. So let's try the limit of the numerator. Well, that would be e to the 0, which is 1, minus 1, which is 0. And let's try the limit of the denominator, which is g of 3x squared minus 4. So that's g of 3. G of 3 is 2. So that's, and then 2 squared is 4, minus 4 is also 0. So we need to apply L'Hopital's rule, so we'll make sure we reference it by L'Hopital's rule. We know that this limit here, and really they should tell us that g is differentiable on some interval around x equals 1, but we can just assume it. Plus, I made this problem, so, I tend to leave out little nitpicky details like that. Certainly, the numerator is differentiable everywhere, though. So the derivative here would be e to the u times u prime. And then let's take the derivative of the problem. We need to use a chain rule. So that's 2 times g of 3x. Remember, the part inside the squared stays exactly the same. Now I multiply by the derivative of g of 3x, which is g prime of 3x. And then again by the chain rule times 3. All right, so now we will evaluate. If I plug in 1 for x, I get 3 to the 0. 3 times e to the 0 is 3, minus 1 is 2. And we know that, let's see here, g of 3 is 2. So that becomes 2 times 2. G prime of 3 is a negative 2, and then times 3, I'll just reduce that. So that makes this a 1 over negative 12. Okay, let's take a look at the next one. For each of the following functions, state whether the mean value theorem and or the extreme value theorem can be applied over the interval. Okay, so for our first one, we have the absolute value of x minus 2. So we know that the absolute value of x is really a piecewise defined function. Okay, let's write that over here. So because two negatives make a positive, if x is negative, then we need to use negative x. And if x is positive, we need to use positive x. So if x is positive, leave it alone. If it's negative, multiply it by negative 1 to flip it to a positive. So the question is, where does this switch from positive to negative? Well, x minus 2 is equal to 0 at x equals 2. For values of x less than 2, like 1, it would be negative. So we're going to use negative of x minus 2 for x values less than 2 and positive x minus 2 everywhere else. So the slope, or the derivative of this function, is negative 1 when x is less than 2, and it is positive 1 when x is greater than or equal to 2. So f is not differentiable at x equals 2. Quite simply, the derivative from the left and right are not the same, so the derivative is not continuous there. But f is continuous on this interval. So the requirements for the mean value theorem is that you must be both continuous and differentiable. You have to be continuous on the closed interval from 0 to 3 and differentiable on the open interval. So the mean value theorem does not apply. Because f is not differentiable everywhere on the interval from 0 to 3. But the extreme value theorem, which guarantees an absolute max and an absolute min must exist, the extreme value theorem does apply. Because f is continuous on that interval. Okay, so that's kind of how that works. Let's take a look at the next one. F of x is equal to the absolute value of x squared minus 9. So x squared minus 9 is a parabola with intercepts at negative 3 and 3, because that's x minus 3x plus 3. And typically we would say that graph would go down and then it would keep going down like this. But because of the absolute value, it's going to reflect it up like that. Okay? So f is continuous everywhere. Excuse me. F is continuous everywhere. But f has places where it is not differentiable at negative 3 and 3. But look what we can say. We can say f is definitely continuous on this interval, right? It's continuous everywhere. And we can say that f is differentiable on the open interval. So yes, it's not differentiable at negative 3 and 3, but this is just asking us if we can use the mean value theorem on that interval. And we can, as long as we're continuous on that interval and differentiable on the open interval. So we can apply both the extreme value theorem and mean value theorem. Okay, let's just take a look at the picture to talk about why, or what we would expect the results to be. You could see that f of negative 3 and f of 3 are both 0. So the average rate of change there is 0. So in fact, we could even say this is Rolle's theorem. So we would expect there to be a horizontal tangent line, and there certainly is right there. Also, we expect there to be an absolute max and an absolute min on this interval. There's an absolute min of 0 and an absolute max of 9. So that happens. Now, the absolute min occurs at two different x values, but it is an absolute minimum of 0. So it can happen multiple places, but we're just guaranteed that it does have a lowest value. All right, let's go on to the next one. The interval from 0 to 4. Well, clearly we are not differentiable at these endpoints, right? But we can apply both theorems because f is continuous on the closed interval from 0 to 4, which is required for the extreme value theorem. And for me to be able to use the mean value theorem, I have to have differentiability everywhere except for those endpoints are not required. So both mean value theorem and extreme value theorem can be applied. And we can see, in fact, that we do have an absolute max. And yet again, we have that same situation where we have a horizontal tangent line predicted by the mean value theorem. And it definitely happens. All right, what about here from -2 to 2? Do you see a point where f is not differentiable, right? So f is not differentiable at x equals 0, but f is continuous on this closed interval. So what that means is we can apply the extreme value theorem, and we say we do have an absolute minimum of 1 and an absolute maximum of something like 2 3/4, somewhere around there. So we definitely can apply that, but we cannot apply the mean value theorem. And in fact, the mean value theorem, the slope of the secant line there is 0. This never has a horizontal tangent line. So mean value theorem cannot be applied due to lack of differentiability on the open interval, but the extreme value theorem can be applied. All right. Practice 7.2. For each of the following functions, state whether the mean value theorem or the extreme value theorem, or both, can be applied, and explain. Okay, let's see how we did on the first one. All right, well, this is clearly continuous everywhere on that interval. Remember, when we're looking for points of discontinuity on a function like that, we're looking usually for things where you divide by 0, or where you're trying to take an even root of a negative number, or logging a negative, or logging 0. But we don't have any of that because we have an odd root. So that means that f must be continuous on that interval. Okay, that's clear. Let's take the derivative here. I don't want to just guess by looking at that. I want to take the derivative. Remember, this is x to the 1/3 power, so this becomes 1/3 x to the -2/3. Well, that, if you allow me to do a little bit of rewriting, is this. Now we still have an odd root because we have a 2/3 for an exponent. So that's not the problem. But now I have a variable in the denominator. So what that means is that f prime of 0 is undefined. So if f prime of 0 is undefined, that means that f is not differentiable at x equals 0. That's what that means, right? So we can apply the extreme value theorem only. Can't apply the mean value theorem because we don't have differentiability from -1 to 1. And you could write all that out, but I'll let you do that. All right, letter B. Okay, so if we're going to have extreme value theorem be applied, we need to make sure we're continuous on the interval from 0 to 4. So this is continuous everywhere, this top branch, the bottom branches. So we need to check what happens at x equals 1. So if I look at the limit from the left, so if we plug in 1, numbers approaching 1 from the left, we would be looking at this top branch, which would be 2, right? And I can just write that like that. X approaches 1 from the left. of f of x is equal to 2. Now, if I look at the limit as x approaches 1 from the right, then I would get, let's see here, that'd be a negative 1 plus 3 again. That's also 2. And so we do know that f of 1 exists. Now we know the limit exists, and they're the same. So we are continuous everywhere on this interval. Question is, what about the differentiability? All right, so let's find out about that. So f prime of x, we need to take the derivative of each portion. So it'll be a negative 1 we're on the left. And on the right, it'll be a negative 2x. And I'll just say x greater than 1, because I don't want to say that I don't want to say greater than or equal to. I check they're the same. Well, you can see that this is not continuous. F prime is not continuous at 1. If you plug in 1 to the top branch, you get negative 1. The bottom branch, you get negative 2. So yeah, this is not differentiable at x equals 1. So again, extreme value theorem only. So the extreme value theorem tells you that you have a absolute max and min. If we wanted to go find them, we would use the candidates test. And that x equals 1 is going to be an important candidate because it was a place where we were not differentiable. So we would check anywhere where the function is derivative is equal to 0, and anywhere where the derivative is undefined. And then we would also check the endpoints, and we'd evaluate them for the maxes and mins. All right, let's try our next one. Ooh, got another little piecewise defined monster here. Okay, first let's check for continuity. This is the cosine, or let's do the top branch here. You know, the limit from the left is 5. The limit from the right, well, the cosine of pi times 1 is cosine of pi is negative 1, and a negative 1 times a negative 5 is a positive 5. So it's continuous. So f is continuous on the interval from 1 to 3. Well, what about differentiability? Well, we can go ahead and talk about it. Let's go ahead and look at it, and then we'll see why it actually doesn't really matter. But let's take a look at the derivative. And that would be a 3 for the top one. And the bottom is going to be a positive 5 pi, because of the chain rule, 5 pi times the sine of pi x. Now, the sine of pi is 0. So this is not differentiable at x equals 1 because the derivative from the right is going to be 0 and from the left is 3. But look, that doesn't matter for the mean value theorem because we only need differentiability on the open interval. So we can say that the extreme value theorem and mean value theorem can be applied. All right, let's try letter D. Okay, first of all, is it continuous? Well, from the left at 1, we get e to the 0 is 1. On the right, I would get 2 minus 1 is 1 to the third is also 1. So it's definitely continuous. And since this point where the function could become non-differentiable, x equals 1 is in this interval, we really need to pay close attention to our derivative here. So my derivative here is derivative e to the u is e to the u prime. So times u prime. And that is going to be for x less than 1. Down here it'll be 3 times 2 minus x, and then squared times the derivative of the inside, which is a negative 1. Okay, and that's for x greater than 1. Now the question is it for x equal to 1 as well? Well, it depends on whether or not these two values give us the same thing at 1. Well, this would give me negative 3, and this would give me negative 3. So it turns out I could put the equal sign in either one of these because it is differentiable everywhere. So f is differentiable on this interval as well. How do I know? Because the derivative was continuous at x everywhere, and particularly in this case at x equals 1. So both mean value theorem and the extreme value theorem apply. I think that'd be a worthwhile one for us to look at a graph of, so let's go ahead and type that in. So I'll do, let's see here, x less than 1. We're doing e to the negative 3x plus 3. Guess I got to put in parentheses. And then, comma, for x greater than or equal to 1, let's do 2 minus x cubed. All right, let's call that f of x. Well, there it is. And you can see that we have a slope, a horizontal tangent line, it looks like at x equals 2. At x equals 1, that's where we're switching, right? So, but the slope is still the same. So we know that we should have an absolute max and absolute min on the interval from 0 to 2. Definitely, somewhere way up here, and then, somewhere it looks like 0 on the 2. And we also should be able to find a place where the slope of the tangent line is equal to the slope of the secant line there as well. But what I wanted you to see is that smooth transition, that local linearity at x equals 1, even though it switches between the two functions, it's absolutely smooth. All right, let's determine, find the value guaranteed by the mean value theorem for e to the x sine x on the interval from 0 to 2 pi. So they're telling us that the mean value theorem must be applied. It's probably a good idea for us to double check. That function is continuous everywhere. Its derivative will also be. So definitely it is applied. Applicable, I should say. So let's try f of 2 pi. Okay. F of 2 pi is equal to e to the 2 pi times the sine of 2 pi. The sine of 2 pi is 0, so that's 0 times anything is 0. F of 0 is e to the 0 times the sine of 0. Well, sine of 0 is also 0, right? So in fact, this looks like Rolle's theorem. But let's go through and make sure that we practice the mean value theorem exactly as it's written. So what that tells me is there must be some value c such that f primacy is equal to f of 2 pi minus f of 0 over 2 pi minus 0. I'll just use x instead of c. I'm a little more comfortable with this. So let's get to the derivative. The derivative is e to the x sine x. That's the derivative of the first. Derivative of e to the x is e to the x times the second sine x plus the first, e to the x, times the derivative of the second, which is cosine of x. And that needs to equal, well, we already discussed that 2 pi is 0, and f of 2 pi is 0, and f of 0 is 0. 0 minus 0 is 0. Well, that's handy because I can factor out an e to the x. E to the x can never equal 0. Nothing to a power equals 0, right? Except for, any non-zero, 0 to the third, I guess, is 0. But you know what I mean? No non-zero number to any power is equal to 0. E to the 0 is 1. Don't forget that. So, yeah, that does not happen. Okay? You could try to take the log of both sides, but the log of 0 is undefined. So all that's left is to solve sine x plus cosine x is equal to 0. This can kind of easily be done just by thinking about it, because if you just move the sine x over, or the cosine x over, what it's saying is, where is sine x the opposite of cosine x? And that's clearly at the pi over 4 angles in the second and fourth quadrant. If you want to go even further, you can divide both sides by cosine of x, and sine divided by cosine is tangent of x. And if you have your tangents memorized, when does tangent equal -1? That is at 3 pi over 4 and at 7 pi over 4. So which one did they guarantee? Was guaranteed? It turns out both of them. We were guaranteed at least one. Both of those values we could call the value guaranteed. The mean value theorem says there'd be at least one. It doesn't say there won't be more than one. But I won't keep going around this unit circle again because that would not be in the interval. All right, determine if the extreme value theorem applies. If so, find the values guaranteed by the extreme value theorem for this equation. So pause the video and please do it your best shot. All right, so the mean value theorem says that if this is continuous and differentiable everywhere on this interval, then we should have a value c such that f prime of c is equal to f of 2 minus f of negative 2. So let's talk about differentiability and continuity. First of all, the denominator, there's a denominator, so we want to check it, is x squared plus 1. Well, that's never negative, and that's never 0. Because you square a number, it becomes positive, plus 1 becomes more positive. So there's no place where this function could divide by 0. If I take the derivative, I got to do the quotient rule. That's low, d high, minus high, d low, all over low, low. Well, all I end up doing is my denominator is just my old denominator squared. So the same thing applies here. So definitely f is continuous on the closed interval and differentiable on the open. In fact, it's differentiable and continuous everywhere. So how does this help me? Well, it tells me that there must be a place where this is equal to the slope of that secant line. So I'm trying to find f of 2 minus f of negative 2 all over 2 minus a negative 2. Well, f of 2 is 4 plus 6 is 10, 11 over 5. All right, f of negative 2 is 4 minus 6 is a negative 2, and a negative 2 plus 1 is a negative 1. Wait, why am I getting 11 over 5 earlier? Hold on. I was doing 2. No, I should be there. 11 over 5. Sorry. What was the numerator on this one? That'd be 4. Negative 2 plus 1 is a negative 1 over 5. Okay, negative 1 over 5. Oh, look at that. Okay. That's going to be a 12 over 5, though. That's ugly. All over 2 plus 2 is 4. So that becomes 12 over 5 over 4, which is 3 over 5, because I can divide the 12 by the 4. So 3 over 5. I was excited. For a minute there, I thought that was going to end up being something nice and easy, but it did not. So it's 3/5. All right, and I've got to solve this, and I will go ahead and distribute. All right, let's go over this one. First of all, we need to see if f is continuous on this interval. That's how we know if the extreme value theorem applies. Well, you look at this, and immediately we have a little red flag because we have a division, and we want to make sure we don't divide by 0. But x squared plus 1 is never negative. If you take a real number and square it and then add 1 to it, you're always going to get a positive number. So there's no problem here with dividing by 0. So f must be continuous. F is continuous on this interval from negative 2 to 2. So therefore, the extreme value theorem applies. If so, we're going to find the values guaranteed by the extreme value theorem. Okay, well, we can find those values. So the way we find those values is we take the derivative, and we use the candidates test. So that's low d high minus high d low all over low, low. So to use the candidates test, we have to evaluate f at the 2 endpoints of our interval plus any critical numbers in that interval. Critical numbers are numbers that make f prime 0 or f prime undefined. you can see that my f prime still has our denominator of x plus 1. Now it's just squared. So it was always positive before. It's still positive. So that's not a problem. So all we need to do is set the numerator equal to 0 and see if that ever is equal to 0. That's because the only way a fraction can equal 0 is if the numerator equals 0. So I'm going to go ahead and expand this out. I don't see any way to kind of factor out right here. So I think I just better expand this out, making that 2. Right, so when we do that, we should get 2x cubed plus 6x squared. It's 2x cubed plus 6x squared. Oh, not 6x squared. 3x squared, right? That is a 3, I believe, right? Yeah, the derivative of the top is 3. So 3x squared, and then we have plus 2x, and then plus 3. And then here, keep that negative. We're going to get 2x times x squared is a 2x cubed, and then plus 6x squared, and then plus 2x. So 2x cubed minus 2x cubed is gone. 3x squared minus 6x squared will be a negative 3x squared. 2x minus 2x is, well, that's gone, right? And let's see here. 3 plus 3, so just plus 3. All right, so solving that equal to 0. Let's see here. I'm going to divide through by a negative 3. I get 0 equals x squared minus 1. That factors as x minus 1, x plus 1. So x equals 1 and x equals negative 1. So to do our candidates test, we simply need to evaluate at each one of these values. I say that as if this is an easy function to evaluate. Probably more challenging than you would expect on like a quick little multiple choice question for sure. But we want to do negative 2, negative 1, and that's what that is. That's a negative 1. We want to do positive 1 and 2. So let's take a look at negative 2. Can't see if we can't figure this out. That would be negative 2 squared. So that's 4. Minus 6 is negative 2 plus 1 is a negative 1. That's a negative 1 over 5. And plugging in a positive 2 won't be too different of a procedure. That would be 4 plus 6 is 10 plus 11 over 5. So that's 11/5. All right, let's plug in negative 1. That would give me 1 minus 3 is a negative 2 plus 1 is a negative 1. 1 minus 3, so negative 1 over, looks like, a half. If I plug in a positive 1, I get 1 plus 3 is 4, plus 1 is 5. So that's 5 over 2. So it looks like our absolute min is at negative 1, negative a half. And the max is at 1 5/2. Or no. Is 5/2 bigger than 11? Yeah, it is. 5/2 is definitely bigger than 11/2. Let's take a look. I have a graph of it here nearby. We can take a look at it and see negative 1 and negative a half, and positive 1 and 2.5, which is 5/2. That is definitely the absolute maximum. All right, for this next one, we're going to use a calculator. I want you to find the dimensions for a cylindrical can of 1,200 cubic centimeters to minimize the amount of material required. But you do have to show your calculus, show your derivative work. All right, let's see how we did that. The dimensions of a cylindrical can. You would be given these formulas, by the way. I just didn't write them down. The area of the can is 2 pi r squared for the lids, plus 2 pi r h for the rectangle that wraps around it. And the volume is pi r squared h. So we know the volume is 1,200. Now I need to solve this for either r or h. I'm going to solve it for h. That's definitely easier because I don't have to deal with the square root. So that makes my area formula, which is what I'm trying to minimize. So I want to get that ready to take the derivative. So I get 2 pi r squared plus 2 pi r times 1200 over pi r squared. And we can just kind of clean this up a little bit here. 2 pi r squared plus 2400 over r. So what I want to do is find the derivative and then solve the derivative equal to 0. So you could, if you have a calculator to take a derivative algebraically, go ahead and do that, or just do it by yourself. 2 n pi are British constants, so this is just 4r. And then that becomes a minus 2400 over r squared, since that's 2400 to the r times r to the negative 1. All right, this is actually not that hard to solve algebraically by hand. You could graph it and solve where the crosses the x-axis. So however you want to do that, I'll go ahead and do it graphically this time. So 4x minus 2400 over x squared. And let's take a look at that. All right, so it looks like 8.434. You do need to be able to do that with a TI 89 or whatever calculator you're using, Inspire. All right, so just out of an abundance of review and caution, let's make sure that everybody's aware of how to do that on like a TI 89 calculator. So I've got like a TI 89 simulator up here. All right, so I just want to go through how to graph that, and let's take a look here. This part of the screen should actually be down here. This uses a ROM skin from your 89. I have an 89, so this is what I'm used to. I'm just using this as an online tool. So if you go to the y equals button, let's see here, escape. Let's see. Diamond y equals, and then we'll type it in as 4x minus 2400 divided by x squared. And there you can check the pretty print, and we'll Diamond F3 will graph it. And we are looking for where we're crossing the x-axis. We can see it there. So we want to go to the math menu, which is F5, and we want to select 2 to find a 0. And lower bound means left. So, it's not always below the x-intercept. It has to be to the left of it. That's the key. In this case, it is below it. But we want to see that little cursor appear on the curve. So I'll just keep going to that little scope and press enter. And then we'll go over here and we'll do it again. And it tells me that's basically 0. It's within the margin of error, 8.434, which I think is what we got before. I just can't read my handwriting. There it is. 8.434. So that, make sure you're able to do that. That is a requirement. This one we could have solved by hand, but they will come up with stuff you can't. So you have to be able to do that. And the nice thing about the graph, though, is you can see that the derivative is negative before and positive afterwards. So we can immediately justify that because a prime is less than 0. Now, it's not defined at r equals 0, but for greater than 0, less than 8.434, and a prime is greater than 0 for 8.434 less than r equals 8.434 locates a minimum. So that definitely would minimize the amount of material, that radius. Throw that in here to find the height that would go along with it. I'll let you do that. All right, so next problem. We have a particle traveling on the x-axis, has its position modeled by the function s of t equals 6t squared minus t to the fourth. Please answer question A and B, and then we'll go over it. All right, we want to find the maximum and minimum velocity. So, of course, the first thing I need is the velocity, which is the derivative of position. So that's 12t minus 4t cubed. But if I'm going to maximize or minimize velocity, I need the derivative of velocity, which is acceleration. I'll just call it v prime since I'm focusing on v. I like to call velocity, the derivative of velocity v prime, when I'm trying to find something out about velocity. If I'm trying to find something out about acceleration, I'll call it acceleration. But you can do whatever you prefer. Okay. So we know that velocity is clearly continuous and differentiable on the slope interval. Therefore, the extreme value theorem, actually just need to be continuous. So the extreme value theorem guarantees that we must have a maximum and minimum. We can use the candidates test to find that. I'll set this equal to 0. I'm just going to go ahead and divide by 12 right off the bat there. And factor this as 1 minus t, 1 plus t. You can see that gives us answers of t equals 1 and t equals negative 1. Well, t equals negative 1 is not in our domain that we're interested in. We're looking at 1. So we'll evaluate at different values of t. We'll evaluate at the endpoints, at our one critical number, and the other endpoint. All right, so I'll start with t equals 0. So v of 0, we're using this function here. Remember, this is the function we're trying to maximize or minimize. This is the function I need to be plugging into. All right? We use the derivative to find our candidates, to find our critical numbers, but we are maximizing and minimizing this. So v of 0 is 0. V of 1 would be 12 minus 4 is 8. V of 4 is, that's going to be a little bit more work. Uh, 48 minus, let's see here. Ooh, that's a big number, right? Because that's 256, I believe. So it would be a negative 208. So we have, this is our max velocity of 8 and our min velocity of negative 208. What was the minimum number of times that the velocity of the particle was equal to 5? Okay, so we know that this graph was going up because the derivative is positive from 0 to 1. And then we know that the derivative is negative again to after 1 and to infinity. So this graph definitely, went up and then started going back down forever, right? And based on the information I have, the velocity was 0 at t equals 0 and 8 at t equals 1. And since the velocity is continuous, it must have gone through 5 there. Likewise between 1 and 4. So I'm going to say by the intermediate value theorem, the IVT, the intermediate value theorem, since v is continuous, and v of 0 is greater, it's not, it is less than 5, and v of 1 is greater than 5, and v of 4 is less than 5, v of t equals 5 at least 2 times. So that's how that goes. All right, let's find some differentials. Let's review that. So pause the video and find the differential for each one of these. Okay, so recall to take the differential is just like taking derivative. You just, instead of writing dy dx, you write dy and put the dx at the end. So dy is equal to, this is arcsecant, another way of writing it, inverse secant. So it'll be 3 times the derivative of arcsecant is u prime over the absolute value of u times the square root of u squared minus 1. So that whole thing is times dx. All right, let's do the next one. We have f prime or we're not going to write f prime. We're going to write, in this situation, let's call it just df is equal to, bring down the 3. 3 divided by 6 is 1/2. So it'll be x squared over 2 minus 3. And the derivative of cotangent is negative cosecant squared. It's going to become a plus cosecant squared x. And that whole thing is times our dx. All right. And I think, yeah, that is it. That was the last little bit of this lesson here, and so that ends up this unit. And I'll see you in the next unit.